The internal combustion engine works by changing heat energy into kinetic energy. There are many ways to do this, some better than others. But no matter how efficiently it is done, and no matter the size of the engine, the heat energy generated never completely changes into kinetic energy. Some energy is always lost. This is certainly true in internal combustion engines, where only about a third of the heat generated is transformed into the mechanical energy that moves the piston and turns the crankshaft. Another third goes out the exhaust, wasted. The rest tries to spread round the engine. Heat always moves from areas of higher temperature to areas of lower temperature, which can be a problem. To control this movement, it is necessary to understand how heat is transferred. Heat travels in just three ways. The way it moves through solids is called conduction. Through liquids and gases, it is called convection. It follows paths called convection currents. Through space, it moves by radiation.
This water is open to the atmosphere or at atmospheric pressure. It is heated and it boils. The thermometer shows its boiling point. Now the water is put under pressure, higher than atmospheric pressure. It's heated and it boils at a higher boiling point. The pressure is decreased. The water again is boiled, but at what temperature? Compare these boiling points. Raising pressure above atmospheric pressure increases the boiling point. Lowering it below atmospheric pressure lowers the boiling point. So changing water pressure can change the temperature at which it boils. Electrolysis is a chemical and electrical process. It occurs when two different metals are in contact in the presence of a moist agent such as water. One of the metals is corroded away. This can occur even in pure water. Immersed in this water are two plates, one of aluminium alloy, the other of cast iron. The atomic structure of aluminium means it loses electrons easily, leaving behind aluminium ions which are positively charged. Negative oxygen ions in the water are then attracted to the aluminium ions, and they join to form deposits of aluminium oxide. As a result, the aluminium alloy is eaten away or corroded. Centrifugal force is a force pulling outward on a rotating body. A vehicle turning a curve is a similar system to this rotating body, so it is subject to centrifugal force too. Centrifugal force resists turning and tries to keep the vehicle moving in a straight line. Centrifugal force is also the force that causes an out-of-balance wheel to vibrate. Centrifugal force can also be useful. When coolant enters the center of this pump and the rotor spins, centrifugal force moves the liquid outward.
Air cooling is common on smaller internal combustion engines. They may be small, but they still generate a lot of heat. It's the air that does the work of keeping them cool, so an air cooling system is usually simple. That's useful on an engine where weight is important, and it works best on the engine that's exposed to a high airflow. Almost all motorcycles used to be air-cooled, but modern motorcycles are larger and more complex, and some are now liquid-cooled. Some engines use what are called cooling fins. Their design makes the exposed surface area as large as possible, which allows more heat energy to radiate away and be carried off in convection currents in the air. More air flows over the fins and more heat is carried away. For a vehicle moving at speed, airflow over the engine is high. At low speeds or during idling, heat builds up. Then the engine can use some help. Air should always be able to flow over the engine effectively. One way to remove heat is to use a fan with shrouds and ducts to direct air to the cylinders. There are many places to mount a fan and many ways to drive it. In this engine, it's on the flywheel. It's driven here by fan belts off the crankshaft. This section examines liquid cooling systems in petrol and diesel engines. In this very basic liquid cooling system, a coolant is stored in a radiator and in the engine. As the engine heats up, a natural circulation starts as coolant rises through the engine block by convection. It passes through the top hose and into the radiator. Inside the radiator, heat is removed from the coolant as it falls from the top to the bottom. When it reaches the bottom, it returns to the engine through the lower radiator hose. This process is called thermosiphon. It was common in older cars which had low-powered engines and high, narrow radiators. In modern cars, the engines are more powerful and radiators are low and wide, and a thermosiphon process couldn't move the coolant quickly enough. Instead, a water pump forces it through passages called water jackets in the engine block. It collects heat and becomes hot itself. Heated coolant then returns to the radiator for cooling. And the cycle is repeated. Heat is removed from the engine and dispersed. Preventing overheating is one function of the cooling system. It also helps the engine reach its best operating temperature as soon as possible. Every engine has a temperature at which it operates best. Below this temperature, ignition and combustion can be difficult. Most engine wear occurs during this warm-up period, and most pollution too. One function of the thermostat is to shorten the warming up period. It operates according to coolant temperature. When coolant is cold, it is closed. When a cold engine starts, coolant circulates within the engine block and cylinder head and through a coolant bypass to the water pump inlet. It can't get to the radiator. As the engine warms up, the coolant trapped in the engine gets hotter and hotter. This starts to open the thermostat, allowing hot coolant to flow to the radiator. Many radiators are mounted at the front of the vehicle in the path of greatest airflow. The air carries heat away, cooling the liquid before it returns to absorb more heat from the engine. Where a radiator is mounted also depends on space, how the engine is mounted. A header tank can be mounted away from the radiator, where it provides a coolant supply stored above the engine. It can be made of sheet metal or hardened plastic. The radiator has two tanks and a core. The materials used in the radiator must be good heat conductors like brass or copper. Brass and copper are often used for tanks combined with a copper core. Modern vehicles often use plastic tanks combined with an aluminium core. This saves weight but still provides good heat transfer. The core consists of a number of tubes that carry coolant between the two tanks. The tubes can be in a vertical downflow pattern or a horizontal crossflow pattern. A crossflow radiator fits more easily under a steeply sloped bonnet. In the core, small, thin cooling fins are in contact with the tubes. The shape of the fins increases the surface area exposed to the air. Where coolant touches tube walls and where the tubes touch the fins, heat is removed from the coolant by conduction, then by radiation and convection at the surface of the fins. Air rushing by carries the heat away. Liquid emerges cooler at the bottom of the radiator. It travels through the lower radiator hose to the water pump inlet, then through the engine again. If a coolant boils, it can be as serious for an engine as having it freeze. Boiling coolant in the water jacket becomes a vapour. No liquid is left in contact with the cylinder walls or head. Heat transfer by conduction stops. Heat builds up, and that can cause serious damage. One way to prevent this is with a radiator pressure cap that uses pressure to change the temperature at which water boils. As coolant temperature rises, the coolant expands and pressure in the radiator rises. It soon rises above atmospheric pressure, and that lifts the boiling point of the water. Engine temperature keeps rising, and the coolant expands further. Pressure builds against a spring-loaded valve in the radiator cap until, at a preset pressure, the valve opens. In a recovery system, the hot coolant flows out into an overflow container. As the engine cools, coolant contracts and pressure in the radiator drops. Atmospheric pressure in the overflow container then opens a second valve, a vacuum vent valve, and overflow coolant flows back into the radiator. And that stops atmospheric pressure collapsing the radiator hoses. Coolant is transferred throughout the cooling system by hoses. Most vehicles have the engine mounted on flexible mountings to reduce noise and vibration. Since the radiator is mounted to the vehicle body, flexible hoses are needed. Coolant is also carried to the heating system, which is usually inside the cabin of the vehicle. Coolant hoses vary in diameter depending on the volume of coolant that passes through them. Heater hoses carry a smaller volume. Most hoses are made of rubber, and since they are subject to pressure, they are reinforced with a layer of fabric. They are moulded to a special shape to suit the model and make of vehicle. Some heater coolant hoses also have special shapes. All hoses are subject to hot coolant and high underbonnet temperatures, and they can deteriorate and fail. The thermostat helps an engine to warm up. It's found in different positions on different engines. It is a valve that operates according to coolant temperature. When coolant is cold, a spring holds the valve closed. When a cold engine starts, coolant circulates within the engine block and cylinder head and through a coolant bypass to the water pump inlet. It can't get to the radiator. As the engine warms up, the coolant in the engine gets hotter and hotter. This thermostat has a wax-like substance that expands as the engine nears its operating temperature. This starts to open the valve. Coolant starts to flow to the radiator. Thermostats have a small hole or valve to let out air that's trapped in the engine block. Heated coolant is pumped from an outlet in the cylinder head. It goes into the upper radiator hose, then to the radiator. The water pump is usually in front of the cylinder block, belt driven from a pulley on the front of the crankshaft. A hose connects it to the bottom of the radiator where the cooler liquid emerges. It has fan-like blades on a rotor or impeller. Coolant enters the center of the pump. The rotor spins and centrifugal force moves the liquid outward. It is driven through the outlet into the cooling passages called water jackets. Water jackets are passages in the engine block and cylinder head that surround the cylinders, valves and ports. Coolant can be directed to hotspots, such as the exhaust ports in the cylinder head, to stop local overheating. Finally, hot coolant is ready to leave the engine. In a vehicle moving at high speed, airflow through the radiator cools the coolant. But at low speed or when the engine is idling, extra airflow comes from a fan. Fans can be driven in different ways. More and more modern vehicles now use an electric fan. Air-conditioned cars often have extra fans. Electric fans can be behind the radiator, in front, or both. This arrangement would be difficult with a belt-driven fan. Some fans can be driven from the crankshaft. When an engine is mounted longitudinally, its fan is usually mounted on the water pump shaft. The drive belt then turns the water pump and fan. Some use a hydraulic link from the power steering system. Fan blades can be rigid or flexible. Rigid blades tend to be noisy and use more energy. This noise can be reduced by using irregular spacing of the fan blades. Some vehicles use a shroud to direct all of the air that the fan moves through the radiator core. At high speeds, plenty of air is already flowing through the radiator. If the fan is always working at full speed, it's a waste of energy. And since the engine drives the fan, it's a waste of fuel too. What's needed is some way to control the fan. A heat-sensitive switch in contact with the coolant can work like a thermostat and turn the fan on and off according to coolant temperature. Another way to alter the speed of the fan is with a viscous hub. This type of fan slips when it is cold, but as the engine heats up, it grips more and more. A recovery system maintains coolant in the system at all times. As engine temperature rises, coolant expands. Pressure builds against a valve in the radiator cap until, at a preset pressure, the valve opens. Hot coolant flows out into an overflow container. As the engine cools, coolant contracts and pressure in the radiator drops. Atmospheric pressure in the overflow container opens a second valve, and overflow coolant flows back into the radiator. No coolant is lost and excess air is kept out of the system. Like water, air contains oxygen, which reacts with metals to form corrosion.
A thermoswitch opens and closes according to preset temperature levels. Some are mechanical, others are electrical. It may be designed to switch off when temperature rises above a certain level, or it can be made to switch on when the temperature reaches a certain level. Heat switches can operate on the bimetallic strip principle. It consists of two different metals or alloys attached back to back. As different metals and alloys heat and cool, they expand and contract differently. That means that if they are joined and then heated, the faster expansion of one will force the whole strip into a curved shape. As the strip changes shape, it can be designed to complete a circuit, and a resulting electrical signal can then do a range of tasks. Or it might have a mechanical effect, simply opening a passageway. Cooling then produces the opposite effect, breaking the circuit and closing the passage.
Overheating can seriously damage an engine. so having warning of trouble is obviously useful. A device that's sensitive to engine temperature sends readings to a temperature gauge or a warning lamp. To give an accurate reading, this sensor must always be immersed in liquid. Indicators that measure coolant levels can give warning if the levels fall too low. In a rotary engine, the rotors are cooled by oil from the lubricating system. Each housing, however, is water-cooled, and there are additives in the coolant to protect the housing alloys from corrosion. The water pump takes coolant from a bottom radiator tank and pushes it through water jackets in the housings towards the rear of the engine. The chamber is surrounded by coolant passages. Inside the housing is hollow, and it forms a water jacket. A pulley on the end of the eccentric shaft drives the water pump and fan. In the rear housing, the coolant reverses direction and returns to the front of the engine. It passes a thermostat. As in a piston engine, it is closed when the engine is cold, but opens as it warms up. The rotary engine has an overflow system much like that of a piston engine. As pressure builds up, coolant expands into an overflow tank. As it cools, pressure drops and it returns to the radiator. A viscous hub links fan speed with engine temperature.